Okay, thank you, Carlos. So, yeah, I'm really thrilled to have Diego Blas as a visitor, Jesus Sierra visitor at the Institute. Some of you already know him. For those of you who don't, let me just say a few words about who Diego Blas is. So Diego Blas is a highly recognized theoretical cosmologist and theoretical astroparticle physicist. He graduated or he obtained his PhD in 2008 from the University of Barcelona, I think, under the supervision of Jaume Garriga. Then he moved for a postdoc position for 3 years to EPFL in Lausanne. Then later 1 year, I think, to NYU, from where he moved to CERN with a junior staff position as the leader of the cosmology group at the theory department of CERN. After that, he was there for 5 years, and then he got the faculty position at King's College London, where he stayed for 2 years. And after these 2 years, he is now moving back to Spain, to Barcelona, with one of these Beatriz Galindo Senior Fellows. Yeah, something I would like to say only, if I had to highlight one specific aspect of Diego that I learned from collaborating with him during these past years and discussing with him, is his high creativity. He has many, many ideas, some of which may sound crazy at the beginning, at least for people like me, but then they lead to very interesting projects. And in particular, he's very interested and has been very interested in connecting problems of fundamental physics to astrophysical and cosmological observations. Thus, I think it's very interesting to have his talk. Only just mentioning he's a Jesus Serra visitors, so he will be here with us for some more time until June 11th. So I hope that many of you could benefit from having him around and invite him to some coffee or something so you can discuss with him. So without further ado, please, Diego, the floor is yours. So
before Diego starts, let me just remind the audience the rules for asking questions, which is just simply that we write the questions in the chat, and then I will mute everyone during the talk, but right after Diego is done with his seminar, then I will mute those willing to ask a question. You can either raise your hand using the Zoom application, or write your question in the chat, or even write the question in the chat of the YouTube channel, or even you can send an email to seminarios@iac.es, and I will try to read the questions from there too. Diego, all yours.
All right. Well, thanks a lot, Jorge and Carlos and everyone for this nice invitation to spend here a couple of months. I'm thrilled to be here, and I am really looking forward to discuss with you any possible ideas to use astrophysics to learn more about nature, learn more about the universe, which I think is one of the most exciting things one can do with data nowadays. As was mentioned before, I'm now moving to Spain, and I hope to be here in the Canary Islands often. So looking forward for new collaborations. I put my picture here. I normally don't do it, right? Because people see you, but yes, you see me in the corridor, that's me, or better, that's me now, right? So I'm really, I'll be very happy to discuss any of the things I will talking about today, or any other ideas we can spot, for possible collaborations, or just, about physics. So first, I want to say that it's great to be back. I was here 20 years ago as a summer student. I was very thankful for this time under the supervision of Badekis and Beckman. I have a proof for that. So this is a book I took 20 years ago from the library. You see, that's me. And apparently it's not very popular, this book, but at least I can say I was here. Anyway, yeah. So my talk is going to be quite informal, as you already have seen. So please, given the format, the question will be at the end, but feel free to ask any kind of questions that may come to your mind. I also understand that the topic is not exactly what is normally discussed in this institute. So apart from 2 days ago. So yeah, and any kind of question is a good question. So first, I want to say a couple of words about fundamental physics from astrophysics. We are living super exciting times in this sense, because astrophysics is getting to the precision that is needed to, learn new facts about, it's getting to the precision to learn precision facts about the universe, right? And in particular, there are many different places where this can be done. I have divided this into 3 places. Well, can you see my pointer? I guess you can, right? Carlos or someone?
Yes, we can.
Okay, yeah. So there are like 3 epochs or episodes of a signal where we can learn something about fundamental physics, and all of them are equally important. So one of them is the emission, right? Here I put, for instance, a binary system with a pulsar and a companion. And you think about a pulsar, or you say AGN, or anything which is extreme, these guys have properties that are completely impossible to get on Earth, like magnetic fields, which are, 10 to the 14 Gauss, or densities of matter of neutrino beams or whatever, which are completely science fiction for what we can do on Earth. So if we can understand this extreme matter with precision, we may ask ourselves, is there something else? Like, is light, for instance, propagating outside of these radio beams, interacting with something in this extreme medium? Is the matter inside of this neutron star, inside of this quasar, really probing new properties of nature? So this is a super interesting question. And we, people like Jorge or myself or Carlos or many others, part of our job is precisely try to find which questions are clean, right? Which questions can be distinguished from astrophysical questions, right? Then the dynamics of this system. So even if the emission is the same, for instance, this pulsar may be orbiting a companion, and this may happen through standard gravitational interactions or through new X dynamics, like you can call it whatever. And this is the same for, again, dense media like dense galaxies, dense between inverted commas, where you can look for, dark matter properties or for new ideas. So that's for the emission. Now there is propagation. So the signal coming from this emitter, again, you can pick up your favorite one, is traveling for many parsecs or for many millions of years until it reaches our telescopes. And in this path, it's feeling the presence of astrophysical environments, but also of other environments, in particular dark matter, for instance. So let's say that you propagate a radio signal and it's intervening with the intervening magnetic fields, with the intervening free electrons, but also is interacting with the intervening dark matter, for instance. Imagine that this dark matter is charged, okay? Why not, right? Maybe that's the way we are going to discover dark matter beyond gravitation, because it may be charged. So it may also affect the signal that is coming to us from whatever source you have. This can be X-rays, gamma rays, radio, microwaves, everything works, right? Everything that gives us a model where astrophysics can be marginalized. Sorry about this. So we are able then to try to uncorrelate other possible signals. Okay, here I put just an example I'm going to discuss later, but let's forget about it for now. Also, we can learn about even gravitational waves, for instance. There are ways in which you have pulsar signals and there are gravitational waves in between you and the signal. Then the signal is going to be modified. Okay, this is a new kind of physics that may appear in your observations. And finally, at detection in your telescopes, if they are so precise, they can also try to look for other changes, okay, having to do, for instance, with the fact that if the emission happened long ago and you are detecting nowadays, if both of these processes are well understood, you may try to also look for things like, I don't know, time-dependent properties of constants or things like that. Okay, so as I said, it's super exciting to explore the frontier between astrophysics and fundamental physics, because this is a super rich field. And as I said, it's clear that at some point we're going to hit gold. It's clear that at some point we're going to hit physics beyond the standard model is through these processes. So this is a picture that is used at CERN sometimes. So here there is the LHC tube, and it is going into the Ballet cluster. So that's like a summary of what we are doing in this effort. And you can imagine a dialogue between the general director of CERN, Fabiola Gianotti, and Zeldovich. And then it can go like this, right? Fabiola may ask, oh, shall we go for larger accelerators? Is that the way to do new physics? And then Zeldovich may answer with a sentence that apparently he actually said, is that the universe is already the poor man's accelerator. So the universe, once you have a telescope looking at your legacy, at your astrophysical processes, it may also be the way to go to understand new physics. So that's a very exciting endeavor. I think we are very lucky that Jorge is, starting this effort here. And I'm pretty sure that this is going to be a super exciting time for everyone. Okay, so that was my motivation, in particular for students to kind of open the, the motivation for why it's super exciting to be doing these things. Now, let me focus on one of the possibilities. Sometimes the problem in this field is to choose what you want to do, right? There are so many possibilities that at some point you have to choose. And dark matter is one of the few, one of the evidences we have that we have to have something beyond our standard model of particles. As Rodrigo said in his talk, our model of particle physics is super complete, but not totally complete. And one of the places where we need new ideas is in dark matter. In dark matter, the first astonishing fact about dark matter is the amount of evidence for the need of something beyond standard model plus general relativity. And this is astonishing because this evidence comes from different scales, right? It's not only one piece of information at one particular scale, right? Like for instance, in the past, the Mercury's perihelion was a puzzle for gravity, and it was solved by general relativity. And this happened at, when potentials became, gravitational potentials became stronger at some particular scale. In the case of dark matter, the evidence comes from such a variety of scales that it's a kind of, not miracle, but it's kind of amazing that a single extra hypothesis, a new particle beyond standard model particles, may explain all of them. So for instance, there are these four different evidences. One of them is the rotation curves of galaxies. So you plot the velocity versus radius of tracers of the gravitational potential in galaxies. You find most of the times, okay, that the tracers trace a gravitational potential that is given by the luminosity, by the luminous matter that you see in the disk, for instance, but at some point it starts going somewhere else. It doesn't trace the potential or the velocity that you would assume for the disk, but you trace something else. And this something else is very well fitted by a halo of dark matter. And this happens, let's say here, I hope you can see, this happens at kiloparsec scales, okay? Now there is other pieces of evidence like the Ballet cluster, where you try to look for where the gas of two colliding galaxies lives as compared to where the gravitational potential is determined by lensing. And you see that one is displaced with respect to the other. And again, this is explained if there is an extra piece of matter that in this process of collision has gone through basically without interacting, right? This is a very famous picture. And this happens at megaparsec scale. So you see, we are going to higher and higher scales. Structure formation, also the way in which you start from a very homogeneous universe and eventually generate a very inhomogeneous universe with the properties that we observe in surveys like SDSS or similar ones. That requires at almost gigaparsec scales, something like dark matter, and finally for the CMB, for the BAO or the CMB, you need dark matter. So there is a lot of evidence, but all of it is gravitational. And you may say, well, with this evidence, it's clear we are going to be able to select a dark matter candidate. We don't really need to be very imaginative about it, right? So now is the question that comes to one. I mean, if you never saw these dark matter models before, you may imagine, well, this piece of evidence is so strong that dark matter is going to be quite boring. It's going to be super determined. And, we can basically just try to determine it through observations. But then you can turn yourself towards the rest of the universe, the one we understand very well, the baryonic part of the universe, which, as you know, in the cosmic pie is only the 5% in energy density nowadays. And you see that this baryonic content is made of very, very, complex structure. There are quarks, there are atoms, there are interactions, there are neutrinos. So is this representative of the whole universe, or dark matter is just an extra particle with the most boring possible properties? Okay, that's the question that, again, is a very natural question. And now we're going to try to see if we can determine its properties through observations. All right. Now, on the dark matter landscape, there are different points for the shopping list. What is a good dark matter candidate? First, it has to be a dark matter candidate. By this, I mean that it has to have a very small pressure. That means that as the universe expands, so this is basically the growth factor of the universe, the energy density should expand as a non-relativistic medium. So something cold, you expand it, and it expands basically with the volume, right? It doesn't redshift. That's, of course, the first thing you have to impose on your models. Second thing, which is necessary, is that this dark matter should be produced in a way which we understand with our physical rules. And Rodrigo spent some time on freeze in, freeze out. So basically, there are models of the hot universe where you can produce relatively naturally dark matter, all right? And those are preferred models also, right? Because those are models that, in a sense, provide you of a mechanism which is natural to not only produce dark matter, but produce it in the right abundance. So these are, I think, the two necessary points for dark matter. And now there are other points which are desirable. So you prefer them when you want to have dark matter models. The next point is this dark matter model also solving other fundamental questions? So is this motivated by fundamental physics? And in this particular, for this particular point, there was a huge activity in the so-called WIMP models of dark matter, the weakly interactive massive particles, which are dark matter models where the candidate is a particle with a mass around the giga electron volt, okay, basically the mass of a nucleon, of a proton, of a neutron. And this is related to some fundamental properties of physics related to also the ways to complete the standard model called supersymmetry. So in this way, there is an incredible connection between particle physics, the fundamental questions of particle physics and the fundamental questions of dark matter. And this candidate may be an answer for both of them. This is a way to go. It has been explored by many observations. And so far, there is no evidence at all about this. I mean, for this to be the preferred candidate. And this opened a kind of crisis in a good sense, a good crisis in the fundamental physics community to look for other candidates, okay? And to basically expand the range of possible masses for dark matter up to basically all the masses that your imagination can handle. So there are models nowadays which are motivated by other fundamental questions in physics, like for instance, string theory, that provide for you dark matter models with masses up to 10 to the minus 22 electron volts. In the middle, there is the so-called QCD axion, which is motivated by one of the passes of the standard model called the Strong-CP problem, which I'm not going to discuss here. But again, there are, in the same way that the WIMP, the point I want to stress here is that in the same way that the WIMP was motivated by fundamental problems or fundamental aspects of the standard model, dark matter candidates with masses so low as 10 to the minus 2 electron volts are also motivated by other fundamental physics, right? And we don't know which one is going to be the right one. So there is in a sense, our task as theorists or our task as astrophysicists is to really try to populate all this landscape with the fourth point, okay, with the possibilities of detecting the different properties of these models. At even higher masses, there are the possibilities that dark matter is made of not particles, but astrophysical objects like primordial black holes. And I'm not going to talk about this at all, but this is a super exciting area with a lot of well, a lot of activity nowadays. But this requires a different speaker. Okay. So I'm going to focus on the ultralight case, okay, and see if we can distinguish it from the high masses, and if we can use your data to pin down the most fundamental property of dark matter. So that's amazing. All these observations that we have, they don't even tell us what the mass of the dark matter is. I mean, it's open to how many? It's open to 30, more than 30 orders of magnitude of uncertainty. All right. So first thing about this ultralight dark matter I want to discuss is I'm gonna use some equations in this talk. I hope they are. I mean, I explained them well enough, but otherwise, please ask me at the end of the talk or one other time. So the massive scalar case may be the simplest dark matter model. So for this, let's take a field, okay? Like for instance, in electromagnetism, you have a vector field which has some Maxwell's equations. There is something simpler than that, which is a scalar field. And the scalar field satisfies, the simplest equation it can satisfy is this one. Okay, an equation where there is a time derivative. So this is the standard box operator over the field. This field may have a mass, okay? And this is a very simple equation of motion. Now, can this act as dark matter? Okay, can this simple equation provide you the first point of the dark matter shopping list? Okay, so for this, we can explore the simplest possible situation where this is a homogeneous field. So let's forget about space derivatives and put only time derivatives. And I'm going to do it in an expanding universe, right? Then you have to put here the Hubble constant that acts as a kind of friction. So imagine then that the universe, inflation or whatever, at the early times provided us some of these fields around us and very homogeneous. So the equation they should satisfy is this one, where dot now is a derivative with respect to time. There are two regimes for this equation. The first regime is where the Hubble expansion of the universe is faster than the mass. So the rate of expansion is faster than the mass of the candidate. Then you can forget about this part of the equation. And what happens then? You see that phi dot is equal to 0 is a solution. Okay, you see that phi dot equals 0, this vanishes, and then the second derivative also vanishes. So you solve this equation. So this field, when the universe expands very fast, wants to be constant. Okay, constant field, right? Constant field. Okay, so this field has some potential like a mass, but at the early times in the universe, it's going to be just doing nothing, stay there. And this doesn't provide any dark matter. What this energy momentum tensor of this guy does is a kind of dark energy. So it contributes to the expansion of the universe, but without giving you the dark matter. So I'm going to explain you a bit more in the next transparency. When does it give you the dark matter? What determines the constant value? Well, it's determined by whatever process you have to generate the primordial value of the field. So normally there is some energy scale. You assume that you expect that this guy is going to acquire this primordial value given by this energy scale that gave you inflation or phase transitions or whatever. Okay, so there's going to be some initial condition, and then this guy stays there as soon as this condition here is satisfied. Now, for the mass of this candidate, which is the important point, there are, in these models that I showed you before, the mass of the candidate is connected to some scale. You can forget about this number here. And then some exponentially suppressed number. Okay, this is what is called a pseudo-Nambu-Goldstone boson. Okay, those are words. The important thing is that these string theory models give you a mass, which is whatever scale you want, suppressed by some exponential number. And this number is very, very, very small. So this number on the exponential is 100 or 200. So that basically means that whatever scale sets the initial condition, whatever scales give you this field, whatever scale string theory prefers, eventually the mass of this candidate is tiny, right? So that's why you can populate these fields at the early times with a constant value that has a very, very small mass associated to it, right? Again, this is, I mean, this is not something that can be understood from my slides, but just the message I think is clear that the string theory provides you with this kind of candidates with a very small mass. This now, as the universe expands, the Hubble rate becomes smaller, right? And at some point it becomes so small that the mass, even if it is very small, the Hubble rate, for instance, today in electron volts is 10 to the minus 33 electron volts. So at some point the mass, okay, it starts to dominate over this term in the equation. And then what happens? Then what you have here is simply an harmonic oscillator, right? So this is the second time derivative, and here a mass. So this is harmonic oscillator. So this guy is going to start oscillating around this minimum with a certain initial condition provided by your early cosmology. You can compute now what happens with the energy density of this field and with the pressure of this field. The energy density is basically given by the value of the field itself. And the interesting point is that the pressure oscillates with the mass of the candidate. So you, in a sense, as you go up and down in this potential, the pressure is also changing sign with this frequency. That means that if you average the pressure at times larger than the 1 over the mass, the pressure is 0, and that's it. That means that this guy has some energy density, whatever it is, provided by the initial conditions, and some pressure that averages to 0. So this is giving you what you want. This is giving you at the homogeneous level a candidate for dark matter. So you don't need to, normally when you think about dark matter, you think about a collection of particles. These field equations also give you an energy momentum tensor, an energy density, and a pressure, which behaves as dark matter. So great, that's a great first point for this candidate. It's very simple. And secondly, when you ask your string theorist friends if they can push a bit harder their cosmological calculations to know which is the current abundance, so which is the relative abundance of this candidate nowadays, okay, what is the final yield of this dark matter model in their string theory models, it turns out that for the mass of 10 to the minus 22 electron volts, for the high energy scale, which is close to the scales which people like in high energy physics, it turns out that for this kind of parameters, the rate and the abundance of dark matter nowadays exactly corresponds to the number that we observe with our current data sets. All right, so this is a kind of miracle also that also in these models, by using kind of natural parameters. So remember that this mass can be very small, that's okay, and that this energy scale is as high as, I mean, it's high maybe for particle physics standards, but not for string theory. So this is very natural. So for these parameters, this candidate is supernatural. Okay, so it's as natural as the WIMP, and that's why there is a lot of excitement nowadays for this candidate. People like Oestreicher or Tremaine or Witten or Lamhui, or myself. No, I'm kidding. We are super excited about trying to understand if we can find ways to pin down if this candidate is the real one for the dark matter puzzle. All right. If this was old, it would be very hard to distinguish this candidate from pure dark matter because, you know, well, if you manage to look at pressure waves, let's say, the scales shorter than this time scale, it would be great, but this time scale, 1 over the mass for 10 to the minus 22 electron volts is some years. So, you know, for astrophysics, I mean, for dark matter phenomenology, let's say, some years is quite a short time. So we need to find other ways to distinguish between this dark matter candidate and other dark matter candidate. And luckily, there is a way to go for this, which is very exciting, which is to look for what happens when you start putting in inhomogeneity. So the equations I showed you before are for homogeneous universe. And now for the dark matter phenomenology, you also need to have an understanding of what happens with the things like the Jeans length, things like, you know, what happens when you start really collapsing dark matter and starting to produce things which are inhomogeneous. In the standard picture, in the standard dark matter paradigm, you can study this very well with a pure perfect fluid without with the pressure, right? As I said, so those are the equation. This is the continuity equation, right? For the pure dark matter candidate in an expanding universe, and here you have the equation telling you how the gravitational potential affect the velocity, right, of this candidate. So this is the standard dark matter paradigm. In the case of this new ultralight dark matter case, what happens is that these equations of the pure dark matter are modified by some extra pieces, okay, that are these ones here. Okay, again, it's you can, I mean, you can trust me in the fact that those appear here. And the important thing is that you can now try to see when is this new piece important. Okay, remember that if you only have this piece here, what you find is the structure, the standard structure formation, okay, where dark matter is collapsing, and at some point, you know, there is some growth of the structure. This growth, you know, starts to generate your galaxy halos because of the gravitational potential. Now there is an extra piece which acts like a kind of pressure, okay, preventing this process to be exactly the same as in the dark matter, pure cold dark matter paradigm. And when is this going to be important? When this is going to be important? When this new piece is of the same order of magnitude as this new piece here, which is the one that also controls the dynamics of the inhomogeneities in the dark matter paradigm. So what is this piece here? It has two velocities, so v squared. It has some derivative with respect to space, so 1 over length. And here, what do you have? You have two derivatives and one more 3. So, 1 over length. So here, this is a typo here. It should be length to the minus 3. And 2 masses in the denominator. And when you want these two guys to be of the same order, what you realize is that when lambda is of the order of the Broglie wavelength of this guy, when lambda is of the order of 1 over the mass of the candidate multiplied by the velocity, then this new phenomenology is going to be important. And when does this happen? Again, and now we start to see some number that we like for 10 to the minus 3 electron volts and velocities of order 1. That will happen for parsec. What's the typical velocity in halos? 10 to the minus 2, 10 to the minus 3. So you see that in this case, for kiloparsec scales, okay, for kiloparsec scales, these candidates of 10 to the minus 22 electron volts are gonna generate something different than the standard dark matter candidates, right? Yeah, since we are taking questions at the end, if this was not clear, I'm happy to come back to this. But again, the take-home message is that this new candidate modifies the standard dark matter equations by a kind of pressure term, which becomes relevant at these length scales. Okay, now you can, as I said, take these equations and solve them in your n-body simulations. This is very tough because you have to solve things with two different time scales. So the one having to do with this short range, in a sense, interaction, and then the whole embody, the whole potential wanted to grow at large scales. So far, there has been very few groups which are brave enough to do this, but the results are also very beautiful. So on the left, I show you the ultralight dark matter simulation. This is a box of 30 megaparsecs. This is a simulation for 10 to the minus 22 electron volts. On the right, I show you a cold dark matter simulation with the same initial conditions. And you see that the structure at large scales is very similar, but on the left, you see a kind of wavy, so it is more dilute, so the structure. And you may already understand why, right? Because when you look at the smaller scales, this guy is gonna be important, so you start making things more fuzzy, okay? Because you cannot really go to very short scales without encountering an opposition provided by this kind of pressure, if you want, right? So you see that the large scale, as I said, is kind of the same, but at the smaller scales, there's a fuzziness in your dark matter model that if you are able to resolve it, is telling you already that your candidate of dark matter doesn't want to go to very, very peaky profiles. That's also why this model of dark matter is called fuzzy dark matter, by the way. All right, here you may be a bit puzzled because I'm starting with this model for dark matter of being a field, and you may wonder, well, but isn't dark matter a collection of particles? Well, it turns out that these two pictures of a field, a scalar field, and the particle picture of dark matter can be reconciled if you go back to the fundamental question that when can you describe a collection of particles as a field, all right? You may think that this is a very fundamental question, but indeed it's something that you're using every day when you use Maxwell's equations and not, a Planck equation, let's say, to describe light. So let's take an example. Let's take our galaxy and try to see when we can describe dark matter in our galaxy as a collection of particles and when we can describe it as a fundamental field. Yeah, I'm doing okay with time, but I have to rush a bit here. So let me ask this question to Planck and to Maxwell. So when you see a bulb, you want to describe it as a collection of quanta or just through a field? So the answer that quantum mechanics gives you is that if you have that all the states of the fundamental particles start to be highly occupied, so every position and momentum state, I start to have many particles on it. In this case, the description in terms of a field is totally okay. Okay, this is something that again is coming from quantum mechanics, and yeah, I'm very happy also to chat about it later on. So let's see if this happens for our galaxy, okay, for these dark matter candidates. So our galaxy, the Milky Way, has a escape velocity of 10 to the minus 3 speed of light. So all particles in our galaxy, all dark matter particles in the halo. So our galaxy has a bulge, it has a disk, and it has a huge dark matter halo of like 100 kiloparsec. And yeah, here it is, 100 kiloparsec. And the escape velocity is 10 to the minus 3, the speed of light. So let's now do a theory's job, and let's take the spherical cow, even worse, let's take a cube cow to describe our galaxy. So in phase space, so in distance versus momentum, what I'm saying is that our galaxy is limited by its maximum size is gonna be 100 kiloparsec, and its maximum momentum is going to be given by the mass of every particle in the galaxy. It's going to be given by the mass of the particle multiplying the escape velocity. So everything which is living here of higher momentum leaves the galaxy. So it cannot be in virial equilibrium. Okay. And now you can say, oh, how many states populate this qubit cow? How many momentum and position states live in our galaxy. All right. For this, you just need to multiply this cube in phase space. So the volume of this cube in phase space and divide it by h bar cube. So h bar is the fundamental quanta for phase space, and it turns out that the number of free states in the galaxy, in the Milky Way, is 10 to the 75 mass of the candidate. Of course, it has to be proportional to the mass, because if the mass is higher or smaller, the volume in this direction is bigger or smaller. So this is the number of free states, is 10 to the 75 mass divided by electron volt to the cube. So it's a huge number. So you have many of them. But now you have to start putting in each of these states particles to explain the mass of the Milky Way. So if you multiply the mass of the Milky Way, so divided by the number of states, and then for each state you give a certain mass, then this number is telling you how many particles you need to put for each state to explain the whole mass of the Milky Way. So this is what is called the occupation number of the state. So you have number of states multiplying by the mass would be the mass that you can explain with one state, with each single state being occupied only once. If you need more than that to explain the mass of the Milky Way, you need to put more and more particles in each particular state, all right? And this number turns out to be what I show here. So if this is bigger than 1, then you should use field equations to describe this dark matter candidate. If this is smaller than 1, you should use particles to describe it. And you see that for particles of masses below 10 to the minus 1 electron volts, the field equations are the way to go. You can, if you want, use quantum mechanics for this. It's up to you, but it would be the same as using, again, quantum mechanics to describe, the light that is now here in this room. It would be a waste of resources. Okay, so in our galaxy, it's totally okay to use classical equations for these dark matter candidates. Okay, so those are the classical equations, and now we can go and see what happens with them. As I told you, this small scale guy is gonna have something to say at kiloparsec scales. So we saw already that the simulations at megaparsec scale look great. Let's zoom in these simulations and see what happens when you start exploring kiloparsec. And when you start exploring kiloparsec, you see that this is, by the way, this showing the density of the dark matter filaments. What you see is at the center of these filaments, there's a huge overdensity, a kind of core, okay? That if you plot in this diagram like radius versus density, what you see is that at large distances, okay, as compared to kiloparsec, the profile is the standard Navarro-Frank-White, so the standard cold dark matter guy, but in the center, there is this troublemaker, or this new term in the equations that generate a core for the distribution of dark matter in these halos. All right, so there is a great opportunity here to distinguish between this Navarro-Frank-White, that would be pure cold dark matter, with this very ultralight dark matter candidate, if you are able to see this core somewhere in your data. Okay, let me skip this. And is this something that is seen? Well, you may know that dark matter in certain dwarf galaxies wants to have a core. Why dwarf galaxies are good? Because they are most dark matter dominated. And you see that there, indeed, there is a collection of data from 6 years ago where the same thing I showed before, but with data, prefers a core, all right, as compared to the pure dark matter, the pure Navarro-Frank-White cold dark matter paradigm. There is also new developments by people here in the institute, putting this data in a bit more cleaner, I would say, analysis, where you see the same R versus rho, and you see that as compared to the cold dark matter paradigm, there is a preference of the density to be cored And that's great, right? Now the question is this core due to this dark matter candidate? Well, here is where the news are not so optimistic, because what you can take from the data is that there is a relation between the density of the core with the radius, okay, with this exponent, and in the ultralight dark matter case, this is not much. Okay, you see that this is a scatter plot, but you know, certainly it looks like the kind of cores that are produced in this dwarf galaxy data are not the ones produced by ultralight dark solid. And here, I think there is a fantastic opportunity for other probes, for other collaborations to try to understand what really is behind this cores. But certainly, ultralight dark matter is not, well, certainly, it doesn't seem to be the answer. Okay. All right, so once we have this core, yeah, I can forget about, since I'm running out of time, let me just tell you what's going to happen with this core. So this core has some properties. It has certain mass, it has certain energy, and then there is the halo of dark matter, which is you know, outside of the core. And in a sense, this core and this halo are talking to each other through gravitational interaction. So what determines the size of the core? It seems, what we found in our paper, that there is a very beautiful relation between the energy per unit mass of the soliton, of this core, as compared to the energy of unit mass of the halo. So if you know the halo, okay, because you determine it through rotation curves, then through this kind of relation, okay, you can predict what the core should be and then try to look for it in data, all right? So you don't need anything else from your observation. So given this relation that, by the way, is not understood, we have not understood it theoretically yet. If you have some dark matter halo with some Navarro-Frank White profile, so the one that cold dark matter generates, then you can predict already which core should correspond to this dark matter halo, and now try to see if you can find this in your data, right? So which kind of data is going to be the first that comes to mind? Rotation curves, right? Because rotation curves may reach small scales. Here, not in this particular galaxy. I'm going to show you those that really go to a small radius, and certainly it's going to be able to say something about if there is some gravitational extra potential in the, you know, at small scales. So for this, I plot you here the profile of the soliton, or the core, and the kind of gravitational potential that it generates, right? And it has some particular rotation velocities associated to it. So this potential from the soliton, from the core, should have a maximum of velocity at a different place than the one given by the pure Navarro-Frank White profile. Okay, and now the stage is set for trying to find this with data. So what we have done is to, yeah, let me skip this. We have basically taken the rotation curve as a function of radius. If you now have a particular galaxy with a, you know, with a dark matter halo of 10 to the 12 solar masses, so you have a Navarro-Frank White here, going up. So at some point there would be this flat region. But if now there is a core in the center, all right, at small distances, this core at some point also generates a maximum in the velocity. And by coincidence, you can see that the maximum of these two should be of the same order of the same order. So the influence of the soliton at the small distances is quite important. Now, this is for 10 to the minus 22 electron volts, and this mass for the galactic halo. If you take a smaller mass, these two peaks start to meet each other, and it's a bit harder to distinguish. Now, with data we took data from this SPARC catalog, which is a great sample in the sense that it goes to very short scales. So this is data, and the data is also very clean. It comes from places where there are not so many variables. And what you see already from this object is that the data, what we do, we take this data, match it to a Navarro-Frank-White profile in the outskirts, and then see what the peak should give you in the rotation curves. And by eye, you can already say that this data doesn't like 10 to the minus 22 electron volts. Okay. If the soliton is, if the mass of the candidate is this one, we are certainly constraining it with data. So we should go to higher and higher masses. Okay. You see, this is basically, and you can do this again with other systems. Oops. When you increase the mass of the dark matter candidate, the soliton becomes more compact. Remember that the influence of the dark matter candidate is 1 over the mass. So you go to shorter distances. And then this means that the soliton is, at smaller distances. So you need better data to determine whether this is or not seen in, whether this is or not the dark matter candidate. But already by eye, you see that 10 to the minus 21 electron volts is totally in tension with the data from this catalog. Of course, in astrophysics, having a single object is not good enough because there may be so many systematics. What we did is we took all the systematic, all the data from this catalog that is good for us, and what we plotted in this diagram, in this histogram, is the relationship between the maximum we expect divided by the maximum of data, well, the other way around, the maximum data divided by the maximum we expect for all the candidates. And you see that if you had this dark matter candidate as your real candidate, this should be 1. So this data should be accumulating around 1. And you see that it's always, in most of the cases, is going towards this picture where the data basically has smaller velocities than the ones predicted by this dark matter candidate. So our conclusion is that this model of dark matter is super highly constrained by spark data, okay, by rotation curves. If you want to go to higher masses, 10 to the minus 21 is quite, disfavored. But you can also try to look for other places where you have data with rotation curves of shorter distances. For instance, the Milky Way. The problem with the Milky Way is that it is a dirty environment. I'm happy to discuss this in the questions, but my conclusion is that the Milky Way doesn't really provide enough cleanness. It's not, as I said in the beginning, you need to, one of the first things to identify in this business is a clean system, and the Milky Way at small distances is not clean enough. All right, so I want to finish with some slide of what we are doing now with the people in the institute. And what we are doing is trying to find these models through a different observation. I'm going to be very fast. So the idea is that I told you that you can describe this dark matter model with a wave equation, right? Plus gravitation. So there are waves, okay, in the galaxy, and these waves interact through gravity. They virialize, but even if they virialize, they are always waves. That means that if you look at what's going on, not at the center, but in the Navarro-Frank-White profile, so at larger distances, the profile is this one, but there are fluctuations of the dark matter field of, with a period given by the mass of the candidate. Because in the end, as I said, those kind of particles, so those kind of elementary constituents of the dark matter field in these models are waves, okay, which fluctuate with the frequency of this candidate. And this opens a huge new world of possibilities to test dark matter if you now consider other observations. For instance, if now the dark matter field is coupled to electromagnetism through this operator, through this coupling, which is basically the field, and here E and B, where E is the electric field and B is the magnetic field. If I'm telling you that dark matter field is oscillating in time, right? It's going up and down with time. Now you take this operator and you see that this is a parity violating operator. So this affects differently the polarization of light. And if you have a source which is super highly polarized, it's propagated through the Milky Way, the plane of polarization, so this initial green line is going to be changing as it propagates in the Milky Way. And as it comes to us, it's going to have a different value, but this value, because we are surrounded by dark matter, is also time dependent. So as we look at this standard polarized source with very high precision, we're going to see that this angle is fluctuating in time. All right. This is an analysis we've done with pulsars in this paper, and we managed to get the best bounds for these super interesting dark matter candidates in this region of parameters. So this is the G I showed you before. So this is an analysis we did, and we are the best for this. But now with Quixote, with Jorge, Tana, and other people, we realized that we may be able to do better analysis. So even better, since we have in-house expertise, we may even design strategies to go for better observational strategies. All right. So I'm gonna finish here. I took almost all my time, but I started a bit late. So those are my conclusions, and I'm very happy to take questions. Thank you very much.
Thanks a lot, Diego. Thanks a lot. Indeed, we don't have much time, but we should speed up a bit in regard of the questions. So the first hand that was raised was by Chris. So Chris, let me see if now you should be able to unmute.
Hi, very nice talk. Thank you. I just had a question about the minimum mass for dark matter halos. So there's also constraints, I believed, on the type of dark matter coming from just the mass function. So is there any minimum mass scale that is predicted in your model, in your type of dark matter?
Yeah, the other constraints coming from the mass function is also the order of 10 to the minus 22, 10 to the minus 21. These models, they have, I think, here. These models, here it is. Yeah, there are other bounds coming from the mass function. Oh, yeah, I cannot show it. You see it here. Coming from Lyman alpha, for instance, observations. The kind of constraints that you get are all the same order of magnitude, 10 to the minus 22, 10 to the minus 21. The good thing is that they have totally different systematics. So in principle, we are complementary.
Okay. So Jorge, now you should be able to unmute yourself.
Okay. Again, thanks for the talk. To the point that I was able to follow, it was clear, very clear for someone that doesn't really know about this thing. So my question I did in the chat already is, the course that you showed from the numerical simulations of ultralight dark matter, these are very different from the ones that are observed.
Yes.
In a way, what you expect is like an Abrahamson and White profile that bends over and becomes flat in a given moment. So it doesn't have this kind of separated structure. Now, one thing that I don't think this simulation has is baryons, and baryons are important in the center. So my question is whether this difference might be due to the need of including baryon physics there and the feedback through gravity with the particles or the fields that you have. So are there numerical simulations where on top of these ultralight particles, you also have baryons?
Right. No, it is very tough.
Well, it would
have
to be done before any conclusion.
Absolutely. No, here the conclusion is that you have pure dark matter. There are these cores. By the way, the core is only this thing. This is the way you attach the. I don't know if I got clear. This is the Navarro-Frank White, and then the core does this, right? And you said that the core doesn't want to do this; it just wants to flatten, right? That's what you are saying, basically.
Yeah. So, but without
it doesn't have this first.
Without including the baryons, it's very hard to make really constraints to reconstraints on the masses. So you might have a very different constraints if baryon physics is included in the simulation.
I fully agree. And let me show you what we did. Here it is, because I had to rush a bit. With our sample, what we did is we took, in this Spark data, you can also know which is the baryon content of the candidate. We took the candidate with less baryon content, okay, or a bit more baryon content, and do this same analysis. And in principle, there are candidates in this data sample with very little baryons, for which, in principle, if there is a core, I mean, there is no core. That's the point. There is no core in them, and baryons, in principle, shouldn't do it because it is, those are the amount of baryons is small. This is basically the amount of baryons as compared to dark matter, and let's say there is no core from baryons and there is no core from dark matter. But it's true that if you want to use this model to explain the cores, then you need the baryons, absolutely, in your simulations. But this is very hard to do, again, because you have very different time scales in the problem. Someone will do it. We are waiting for the results. I can't tell you more about baryons, but analytical.
Okay, thank you.
So I next move to Alexander's question. Alexander, now you can unmute yourself, I think. Yes.
Yeah, thank you, Diego. It was really very clear presentation. And I fully agree with Jorge that for someone like me that is not familiar with this field, it was really very easy to follow. So my question is basically connected with Jorge's question. I mean, it's true that the baryons dominate, particularly in the centers of the most massive galaxies. So did you try with these massive galaxies?
Precisely, the problem, we want to avoid baryons precisely because of this. We don't have the simulations yet. So if we start mixing with baryons, we are gonna, it's gonna be very hard to distinguish between dark matter properties. That's why, as I said, in the sample we used, we tried to marginalize over baryons by doing this, by choosing those with less baryonic content. Let's take the Milky Way, for instance, okay? We all agree that the Milky Way has many baryons in the center, all right? And in this case, you can take the enclosed mass, all right, as a function of radius. At short distances, what you see is Sagittarius is A star, so the black hole in the center. And at some point, you start seeing that the traces of the mass start to track baryons. And then precisely here, the influence of the soliton would be exactly, marginal with what baryons do. So for instance, with the Milky Way, we cannot say much. Absolutely, if there are simulations with some baryonic content, at some point you can use them for this, or with black holes in the center, for instance.
Mm-hmm. No, but it's nice to see the separation you did here, no? You show here, no? For the black hole and the Mm-hmm.
Exactly, and this would be the 10 to the minus 21, for instance, would give you this bump, but of course there is also a nuclear bulge in the galaxy, and it can be anything.
Mm-hmm. Thank you.
Thank you.
All right, so John, you can unmute yourself if you want to ask the question, otherwise I can read it.
Well, my question says, is one advantage of this type of models the fact that the particles themselves cannot be detected by the usual techniques of particle detection in the laboratory?
Absolutely. Well, I don't know, you can see my hands, but when you think about the standard dark matter laboratories to detect dark matter, normally what you have is the dark matter hits your detector, and then the detector needs some energy, needs some momentum to get excited, right? So and this momentum is kilo electron volts. So if you have the mass, the typical velocity of the dark matter candidate is 10 to the minus 3, and the mass giga electron volt is going to be the mass that can hit your detector efficiently. Anything below giga electron volts or mega electron volts is very tough to detect on the lab. On the other hand, precisely because we have this, what I say here, these fluctuations of the galactic field of the dark matter, which are very coherent, you can now try to find other ways to detect dark matter, not through the standard detection, but through, I don't know, trying to look for instance, fundamental constants in atomic clocks that oscillate with time. So it's a very exciting field nowadays in particle physics. Precisely, how do you go beyond the huge one-tone detectors to something which is very precise also for detection?
Okay, thanks. Very, very interesting. Thanks.
Diego, there is another question by Isaac Alonso, who cannot use his mic. I'm just reading the chat for you. He says, thanks for the talk. Sadly, I cannot use my mic. When referring to the small timescales needed to resolve in the simulations, what order of magnitudes are they?
Well, you see it here. Basically, you need something that resolves kiloparsecs. Well, this is what I showed here, basically. Yeah, you need something that resolves kiloparsecs. And in time scale, this is something that resolves from gigayears to hundreds of years, in a sense. So, yeah. Not easy.
Yeah, it's 8 orders of magnitude. Okay. Yeah, I see not easy at all.
Unit tricks for this. Yeah.
I have my own question. Well, I have many questions actually. One, probably the first one that I arose is, I once listened to a talk by Tom Broadhurst on bosonic dark matter, right? He was actually not solving the Klein-Gordon equation that you were solving, but a Schrödinger equation.
Yes.
And you know, it was apparently, you know, the change of character or the change of nature of his candidate for dark matter was that it was a boson, not a fermion. Therefore, you have solitons, you have waves at the centers of the halos. Is it the same? I mean, is there any difference?
It's the same.
Is it exactly the same? Because
the Schrödinger equation appears when you take the non-relativistic limit of the
Klein-Gordon equation.
Klein-Gordon. Yeah.
Okay.
I didn't explain it here, but I'm happy to explain it. You take the Klein-Gordon field and you expand it as something which oscillates fast and a slow oscillation, right? Well, as something that oscillates slowly, let's say non-relativistically, then the question for this part is Klein-Gordon. Yeah.
Okay. Okay.
And they claim that they have seen the soliton in the Milky Way, but I have my doubts.
Okay. You said once that you were finding in one of your latest publications some type of equipartition, energy per particle equipartition that you could not understand. How? No. So if you could not understand, how do you get to it? So
because we just plot it.
Okay.
Yeah, it is here.
So it's out of the data or what?
It's from the simulation. You take the simulation, you take the energy of the halo divided by this mass, the energy of the soliton divided by this mass, and you find this relation. So it looks like the soliton is kind of interacting, is relaxing in a sense with the Navarro-Venn-White profile. The reason why this is not easy to understand is that if we now, and we are coming to various now, if you put extra potential now, if you put some stars in these simulations, people have done it, and what you see is that this relation, okay, is altered in a way that, well, this requires more time, Carlos. We can talk about it, but we don't really understand where this comes from.
One last question. Here you're hammering the rotation curves to probe the dynamical profile or the potential profile to probe this type of
basically to exclude the presence of cores.
Right. Is lensing of any use here? Gravitational lensing?
Yeah. But then you need to have a short. Well, that comes also to the questions that were asked before. So you need to find lenses where you are confident that there is a core. Okay. Now, if you are using big galaxies, then there will be baryons. It's going to be a mess. Right. So you need to see if you can go to these small objects, let's say, where there are not so many baryons for lensing. And I'm sure that people in the institute know way more than me about this. And I'm also I know the references for this, so we can discuss it later. But to me, it is a bit more dirty because the typical lens is not only, I mean, in the center in particular, for some micro lensing things, you need I mean, to model the values. But if you model the values well, we may be able to say something about it.
Cool, cool. Let me check if there's any. So in the chat, in the YouTube chat, there are no questions. Let me check the email. Actualizar. No, nothing new. All right. So I think, yeah. So Ricardo, Tana is congratulating you. It was a very nice talk indeed. It was a very nice, comprehensive talk. It was a very nice introduction, Diego. Thanks so much. So unless anyone else wants to ask any other question, people are clapping.
Yeah, I want to share for the last time our amazing future.
Oh yeah. Let's see if you guys manage to get out of Quixote. That'd be awesome. All right. So yeah, thank you, Diego. Thank you, everyone. So yeah, let's wrap it up here and talk to you soon in the next seminar.
I'm here for a month. Yes. Okay.
All right. Yeah. So you're staying here until June what?
11th. Yeah.
11. Great. So you will see you around. Okay.
Cheers. Bye-bye.
Bye.